Imagine looking out your window, at an empty, muddy dirt lot.
Okay, setting the scene.
Yeah. You pack your bags, you go on a 3-week vacation, and, well, when you get back, you look out that same window, and there is a fully finished 57-story skyscraper sitting exactly where that mud used to be.
Which just sounds like a glitch in the simulation, honestly.
Right, it sounds like pure science fiction. But today, we're going to look at how the physical world, like the incredibly stubborn, slow-moving reality of dirt and steel and concrete, is being manipulated at speeds that seemingly break the laws of traditional physics.
It really does force a complete recalibration of what we consider possible.
Yeah.
I mean, we've been conditioned to accept that building heavy infrastructure requires decades.
Oh, absolutely.
We expect, environmental reviews, community pushback, endless geological surveys, years of traffic diversions just to get a single highway overpass built.
Yeah, just dealing with the cones and the detours forever.
Exactly. So the idea of raising a skyscraper in 19 days or sinking a massive tunnel under the ocean in just a few years, it fundamentally disrupts our baseline expectations of time and engineering.
And that disruption is basically the core of our deep dive today. So welcome to the conversation. We're talking directly to you, the listener.
Whether you're navigating a commute or, analyzing supply chains for work.
Or just intensely curious of the hidden mechanics of the modern world. Our mission today is to unpack this fascinating document. It's titled 10 Large Complex Projects Over the Last 10 Years That Stood Out for Their Scale and Relatively Rapid Execution.
Quite a mouthful of a title.
But it is, yeah. But we are going to deconstruct the engineering, the logistics, and really the sheer audacity required to execute these massive physical feats between the years 2016 and 2026.
And the author of this document actually opens with a highly provocative philosophical framing, which I found really interesting.
Oh, the age of abundance thing.
Yes, exactly. Before they even list a single project, they introduce this concept of an impending age of abundance, noting that, such an era has been prophesied in various scriptures and philosophies for millennia.
Right.
By starting there, the author isn't just cataloging construction sites. They're suggesting that humanity's ability to manifest its physical needs is finally catching up to the speed of our imaginations.
It's a super bold premise. I mean, if we can think of a 100 million passenger airport, we can just sort of manifest it in 3 years.
Yeah.
But to ground that philosophy, we really have to look at the cold, hard reality of the dirt.
Right, the actual logistics.
Exactly. So we're going to examine a heavy concentration of centralized projects in China, along with vital examples from India, Ethiopia, and Iraq. And before we get lost in the awe of the engineering, I think we need to establish the central tension running through this entire source text.
Yeah, and that tension is the cost of velocity. Because when you accelerate the manipulation of the Earth to this degree, you are dragging materials, logistics networks, human physical endurance, and local ecosystems right up to their breaking points.
The absolute limits.
Exactly. We are balancing the breathtaking awe of record-breaking speed against the profound, systemic trade-offs required to actually fuel that speed.
Well, let's test that tension immediately. The source starts by looking at the infrastructure that connects the globe, specifically highlighting the Beijing Daxing International Airport.
Daxing, yeah.
Built in China between 2014 and 2019. And the scale is almost comical. We are talking about a terminal covering 700,000 square meters.
To contextualize that, because numbers that big sort of lose their meaning, 700,000 square meters of terminal space means the internal climate control alone requires an HVAC system the size of a municipal power grid.
Wait, seriously?
Yeah. They had to design and install air circulation for a space capable of holding small weather systems, and they were doing it while the roof was still being built.
That's insane. And it's a star-shaped design, right? By Zaha Hadid Architects, utilizing over 52,000 tons of structural steel.
Yeah.
And yet the main structural build took roughly 3 to 4 years, with operations starting 4.5 years after ground was broken. I'm looking at the logistics of this, and the math just doesn't seem to work for me.
How do you mean?
Well, you have 52,000 tons of steel. You have a peak workforce of 40,000 people. How do you even put 40,000 workers on a single site without them just, trampling each other?
Right. And that is the invisible engineering of megaprojects. It's the urban logistics of the workforce.
Yeah.
Because 40,000 people, that is a medium-sized town.
It really is.
Before you pour a single foundation for the airport, you have to build temporary housing. You have to establish a massive industrial catering operation capable of serving over 100,000 meals a day.
Oh, wow.
Yeah.
100,000 meals.
Yeah, you have to feed them. And lay temporary plumbing for sanitation, create a localized traffic grid just to move workers from their bunks to their specific zones on the site. I mean, if the shift changes aren't choreographed flawlessly, you lose tens of thousands of man-hours just to foot traffic jams.
So they've essentially built a shadow city just to build the airport.
Exactly.
But even with infinite labor, traditional construction requires a sequence, right? You clear the dirt, you lay the foundation, you frame the walls, you build the roof. The source notes they used parallel work streams. How does that actually function physically?
It requires completely abandoning that sequential mindset. At Daxing, the runways, the subterranean high-speed rail tunnels passing beneath the terminal, the road networks, and the terminal's steel superstructure
Yeah.
were all under construction simultaneously.
I'm trying to picture this. It sounds like compiling the software while you are still writing the underlying code.
That's actually a great analogy.
Because if you are building the rail tunnel directly underneath the terminal while you are hoisting 52,000 tons of steel above it, doesn't the heavy machinery vibration from the tunnels compromise the, millimeter precision required to bolt the roof nodes together?
It absolutely threatens to.
No.
Which is why the source emphasizes their reliance on advanced modular prefabrication.
Well, prefabrication.
Right. They were not out there cutting and welding individual steel I-beams 150 feet in the air while dump trucks rattled the ground below them.
That sounds like a disaster waiting to happen.
Exactly. Instead, they manufactured massive, complex structural nodes off-site in specialized fabrication yards. They brought these pre-engineered components in, hoisted them with heavy lift cranes, and just locked them into place.
Like giant puzzle pieces.
Exactly.
Yeah.
The tolerances were calculated digitally long before the steel ever arrived at the site.
And the source points out that achieving this level of synchronized chaos requires a really specific administrative environment. Daxing was a strict, centralized national priority.
Which serves as the ultimate logistical lubricant, honestly.
Yeah.
When a project carries that designation, the supply chain is essentially guaranteed by the state. If they need a specialized crane, it is requisitioned. If they need raw steel, the mills prioritize that order above all others.
So all the red tape just vanishes.
Exactly.
Yeah.
The typical friction of zoning disputes or funding freezes or local municipal disagreements, it simply evaporates.
Which brings up a fascinating contrast, actually, because the source immediately transitions to Project 5.
The Navi Mumbai International Airport.
Right, in India, with the main construction happening roughly between 2021 and 2025. And here, we aren't looking at a purely state-run directive. It's a public-private partnership.
Right, PPP model.
Yeah, PPP involving the Adani Group, CIDCO, and the contractor Larsen and Toubro. And their geographical starting point was incredibly hostile.
Hostile is an understatement, honestly. They started with 1,160 hectares of undeveloped land, but it wasn't flat, stable earth. The text notes they had to reclaim marshland and completely flatten an entire hill just to make room for this Lotus-inspired terminal.
I really want to stop on that detail, because flatten a hill and reclaim a marsh sounds like a neat little bullet point on a slide.
Right.
But the geotechnical reality of that is terrifying. You can't just pave over a swamp and land a 300-ton Boeing 777 on it. The soil will compress, the runway will buckle, and you have a massive catastrophe.
You're touching on the exact science of soil consolidation there. To turn a spongy marsh into an international runway, engineers utilize techniques like wick drains.
Wick drains, how do those work?
They push thousands of long, perforated plastic tubes deep into the muddy earth. Then, they pile hundreds of thousands of tons of sand on top of the site.
Just burying the marsh in sand.
Exactly. And the sheer weight of that sand creates immense downward pressure. It forces the water that's trapped in the deep soil to travel up those plastic wicks and drain away. They were literally squeezing the water out of the Earth's crust to force the soil to settle and compact in a matter of months, rather than waiting, decades for it to happen naturally.
So they are artificially accelerating geology.
Precisely. And while they are doing that in the marsh, they are running continuous blasting and hauling operations to erase the nearby hill, and then using the blasted rock as fill material.
It's so resource intensive. But doing all of this within a 3 to 4 year intense build window in a PPP model is historically unusual for India, right? I mean, they've often faced massive delays in infrastructure. How did this partnership actually accelerate the timeline?
The source identifies a pivotal shift post-2022. It points to the sudden acceleration of land acquisition and resettlement.
Ah, okay.
In many democratic or mixed economy systems, acquiring the land from private owners and relocating communities, that's a decade-long legal battle.
Right, the eminent domain process.
Exactly. But once the government side of the partnership pushed through that specific bottleneck, the private contractors were unleashed to apply what the text calls highly focused phasing.
Focused phasing, meaning they aren't trying to unveil a 90 million passenger facility on opening day.
Right. They isolate phase one. They focus entirely on getting the runways operational and a terminal ready for about 20 million passengers.
So they get it working and making money first.
Yes. By structuring the project to deliver a functional, revenue-generating asset rapidly, they secure the cash flow and the public momentum needed to continue building the subsequent phases.
That makes a lot of sense. So with Daxing and Navi Mumbai, we see two different administrative approaches, the state directive versus a PPP, but both are utilizing intense mobilization and modularity to conquer dry land and swamps.
Yeah.
But what happens when the land simply runs out? I mean, when the thing separating two massive economic hubs isn't a hill you can flatten, but miles of hostile, deep, typhoon-prone ocean.
Well, then you are forced to shift from earthworks to deep water marine engineering.
Yeah.
And the forces involved there, hydrostatic pressure, corrosive saltwater tidal currents, that make a marsh look like a sandbox.
Right. Which takes us into the second major theme of our deep dive, conquering the sea, focusing on immersed tunnels and artificial islands.
A huge leap in complexity.
Absolutely. The text highlights Project 2, the Hong Kong-Zhuhai Macau Bridge, or HCMB, built between 2009 and 2018. It spans roughly 55 kilometers. You could literally run a marathon across this thing and still have miles to go.
And crucially, it is not just a bridge.
Right.
To maintain an open, deep-water channel for the massive cargo ships navigating the Pearl River Delta, a 6.7-kilometer section of this crossing had to dive down and become an underwater tunnel.
Oh, wow.
And to bridge the gap between the sky and the seafloor, they constructed massive artificial islands in the middle of the estuary to serve as transition points.
The specs on this are just wild. It's designed for a 120-year lifespan, engineered to resist severe typhoons, earthquakes, and the direct head-on impact of a stray cargo ship.
Yeah.
And they built the main structure in about 8 to 9 years. But how do you build a 6.7-kilometer tunnel at the bottom of the ocean? You can't bore through the mud down there without catastrophic risk.
Oh, no, you avoid boring entirely. The source points to the use of immersed tunnels, which is a technique that essentially turns civil engineering into shipbuilding.
Shipbuilding.
Yeah. They constructed 33 individual tunnel segments on dry land inside massive, climate-controlled factory environments.
I'm trying to visualize the scale of a segment here.
Okay, imagine a hollow concrete box, but it's the size of an aircraft carrier.
An aircraft carrier.
Yes. A single segment weighs tens of thousands of tons.
Okay, wait. If it weighs tens of thousands of tons, how on earth are they moving it from a factory on land into a trench at the bottom of the ocean?
They utilize Archimedes'
A
principle.
buoyancy thing.
Exactly. Even though the concrete is unimaginably heavy, the hollow space inside the sealed segment displaces a volume of water that weighs even more than the concrete itself.
Oh, that's brilliant.
So they seal the ends with massive watertight bulkheads, and the segment becomes buoyant. They literally float a piece of a highway out into the middle of the ocean using specialized tugboats and marine pontoons.
So they basically have an aircraft carrier made of concrete bobbing in the waves. Then what?
Well, meanwhile, massive dredging ships have carved a highly precise trench into the seabed below. They position the floating tunnel segment directly over the trench. Then they begin pumping water into carefully designed internal ballast tanks.
Sinking it on purpose.
Yes. As the segment becomes heavier than the water it displaces, it begins to sink. And they use GPS and acoustic transponders to guide it down through the murky water with millimeter precision.
But I'm stuck on the connection point.
Okay.
You have a sunken tube sitting in the mud, and you sink the next one behind it. You are working under immense hydrostatic pressure in pitch black water. How do you seal two concrete blocks together underwater so tightly that a 120-year lifespan is guaranteed? Because if water gets in, people driving through the tunnel drown.
The sealing mechanism is actually brilliant. On the end of the segment, they install a massive continuous rubber ring called a Gina gasket.
Okay, a giant rubber ring.
Right. And when the new segment is lowered, hydraulic jacks pull it flush against the previously sunk segment, so the two bulkheads meet, with the rubber gasket between them.
But hydraulic jacks aren't strong enough to permanently hold against the ocean.
They don't have to be.
Yeah.
The engineers just pump the trapped water out of the small space between the two bulkheads.
Oh, I see.
Yeah. The moment the space is emptied, the ocean's immense hydrostatic pressure pressing on the outside of the newly sunk segment acts like a giant invisible hand.
Wow.
The ocean itself shoves the new segment forward, violently compressing that massive rubber gasket and creating an impenetrable permanent seal. They literally use the hostile pressure of the sea to lock the tunnel together.
That is astonishing. They weaponize the ocean against itself.
They really do.
And they managed all this while navigating 3 different legal jurisdictions: Hong Kong, Macau, and mainland China, for an investment of roughly $18 to $20 billion.
It was a monumental achievement of parallel execution in a marine environment. But, as the text shows us, the HCMB was essentially a warm-up.
The warm-up.
Yeah, because it paved the way for Project 3, the Shenzhen-Zhongshan link,
Yeah.
built from 2017 to 2024.
Oh, right. Yes. Another massive 8-lane sea crossing, ranging from 24 to 50 kilometers depending on the road network, featuring 2 more artificial islands and an immersed tube tunnel that breaks records at over 6.8 kilometers wide and long.
And the timeline here shrinks again, 7 years.
Yeah, dropping the travel time between these 2 massive cities from 2 hours to 30 minutes.
They essentially welded 2 metropolitan economies together by sinking concrete into an estuary.
But I have to push back here, because we're talking about a 120-year lifespan in a region battered by typhoons. When you accelerate an underwater project to this degree, sinking massive tubes and building artificial islands in 7 years, doesn't speed inherently become the enemy of quality? It feels like building a house of cards in a wind tunnel.
It is a highly intuitive fear, I totally agree. Rushed concrete often means weak concrete. But the text reveals that prefabrication is the shield against that risk. It fundamentally relocates where the hardest work is performed.
What do you mean by relocates?
Well, if you try to pour and cure concrete out in the middle of a saltwater estuary, you are fighting humidity, violent temperature swings, driving rain, and the constant vibration of the waves.
Which concrete hates.
Exactly. Concrete needs specific conditions to cure strong. If you pour it in a hostile environment rapidly, it will be riddled with microscopic flaws.
So the speed would destroy the integrity.
Yes. But with immersed tubes, they aren't pouring concrete in the ocean. The ocean is just the delivery site. The pouring happens inside those massive climate-controlled factories on land. The engineers can control the ambient humidity to the single percentile.
Yeah.
They use automated vibration machines to eliminate every microscopic air bubble. They test the steel rebar with lasers before a drop of concrete even hits it.
So the environment is flawless.
Exactly. The prefabrication allows them to perform the quality control heavy lifting off-site under perfect laboratory conditions.
I see. So the speed we observed out on the water, floating it out and sinking it, is an illusion. It looks fast because we are only watching the final assembly. The real painstaking, time-consuming chemical perfection happened months earlier on land.
Precisely. By the time that segment floats out to sea, its 120-year structural destiny is already locked in. The specialized marine vessels and the 247 shifts are just a highly optimized delivery mechanism.
That completely reframes the concept of rapid execution for me. It's not about working faster in the elements. It's about removing the elements from the equation entirely. But speaking of the elements, sinking concrete into the ocean is about finding a way to slip past the water or bridge over it. You are coexisting with the environment. What happens when the infrastructure isn't designed to coexist, but to completely halt and dominate the kinetic energy of an entire river system?
Then you are shifting from transportation to energy generation. You are stepping into the arena of megadams, where you face the rawest physics of mass and gravity.
Well, let's transition to subsection 3 of our analysis, harnessing nature.
Okay.
The source provides a jaw-dropping example with Project 4, the Wudandi hydropower station in China, built from 2015 to 2021. The sheer capacity is 10.2 gigawatts from 12 generating units, blocking the high-altitude Jinsha River.
Just for some context on that power output, a massive multi-reactor nuclear power plant might generate 2 or 3 gigawatts.
And Wudandi is generating over 10.
Yeah. It is a towering monolith of concrete jammed into a steep, remote mountain gorge.
And the timeline is the most shocking part. Construction started in late 2015, and all units were operational by mid-2021. Roughly 5.5 to 6 years to build a mountain of concrete.
which is incredibly fast for a dam.
Right. Now, based on what we just discussed about prefabrication, you can't build a dam in a factory and float it down a river.
No, you definitely cannot.
You have to pour millions of cubic meters of concrete directly on site, right in the gorge. So how did they bypass the environmental delays we just talked about?
The source highlights a massive technological enabler here. It specifically credits the use of specialized low-heat concrete combined with real-time sensors and cooling.
Okay, low-heat concrete.
Yeah, and to understand why this shattered the timeline, we really have to look closely at the thermodynamics of concrete.
Let's get into the chemistry, because most of us just assume concrete, dries out in the sun.
Right, but it doesn't dry. It cures through a chemical reaction called hydration. When water mixes with cement compounds, it creates calcium silicate hydrate, which binds the sand and gravel together into artificial rock. Okay, but this chemical reaction is highly exothermic. It releases a massive amount of energy in the form of heat.
Wait, really? Because if I pour a patio in my backyard, I don't feel it getting hot?
Because a 4-inch patio has massive surface area relative to its volume, the heat dissipates instantly into the air.
Oh, I see.
But when you are pouring a solid monolithic block of concrete that is hundreds of meters thick, like the base of a dam, the heat gets trapped in the core. The internal temperature can skyrocket well over 150 degrees Fahrenheit.
Wow. And I'm guessing that heat creates a structural problem.
A catastrophic one. As the core blazes with heat and tries to expand, the outer layers of the concrete against the cold river air cool down and contract.
Oh, so they are fighting each other.
Exactly. This massive temperature differential creates severe tensile stress. The concrete will literally tear itself apart from the inside out, creating deep thermal cracks.
That sounds bad.
If you were trying to hold back millions of tons of river water, a cracked dam is a death sentence for everything downstream.
So how did engineers historically deal with this thermal cracking risk?
Through agonizing slowness. They would pour a very thin lift of concrete, maybe just a meter or two high. Then they had to stop operations entirely.
Just wait for it to cool.
Yeah, they would wait weeks, sometimes months, for that specific layer to chemically hydrate and naturally radiate its heat into the atmosphere before they dared to pour the next layer on top.
So the thermodynamic limits of concrete basically dictated a decades-long construction schedule.
Exactly. The material itself was the speed limit.
Okay, so what did the engineers at Wudongdi do? How did this specialized low-heat concrete and real-time cooling actually work in practice?
They attacked the problem on two fronts. First, material science. They engineered a specific blend of cement that chemically releases significantly less heat during the hydration process without sacrificing compressive strength. Second, and more radically, they turned the dam into a smart living machine while it was being built. As they poured these massive blocks of concrete, they embedded thousands of kilometers of cooling pipes and highly sensitive digital thermometers directly into the structure.
So they essentially built a liquid cooling system, like in a high-end computer or a car radiator, right into the stone.
Exactly like that. As the real-time sensors detected the core temperature of the curing concrete beginning to spike, automated systems would kick on, pumping chilled river water through those embedded pipes.
Oh, wow.
They were dynamically drawing the heat out of the concrete's core in real time. By artificially flattening the temperature curve, they completely eliminated the need to stop and wait. They could pour continuously, lift after lift, month after month.
That is phenomenal. They literally manipulated the thermodynamic properties of the material in real time.
Yep.
Paired with a peak workforce of over 70,000 jobs per year and modular Taran components pre-assembled by the state-owned China Three Gorges Corporation. Well, that explains the 6-year timeline. They engineered their way out of a chemical bottleneck.
It is a triumph of advanced engineering combined with overwhelming labor force. But, as the source text crucially points out, not every bottleneck can be solved with chilled water and 70,000 workers.
Right.
Sometimes the constraints are not chemical, but geopolitical.
Absolutely. And this takes us to Project 9 on the list, the Grand Ethiopian Renaissance Dam, or GERD, built in Ethiopia with massive phases running from the early 2010s well into the 2020s.
Yeah.
The text notes that while it utilized modern techniques, and it actually mentions international and Chinese involvement in later stages to accelerate concrete pouring, its overall timeline does not represent the pure, unadulterated speed of the Chinese domestic projects.
And the source specifically identifies why.
Right.
The extended timeline for GRD was heavily impacted by complex international diplomacy, geopolitics, and depth disputes with downstream nations over the filling of the reservoir and water rights.
It's a fascinating inclusion by the author. It highlights that infrastructure is never built in a vacuum. I mean, you can have the most advanced low-heat concrete in the world. But if the river you are damming crosses international borders and affects the agricultural survival of millions of people downstream, diplomacy becomes your ultimate supply chain constraint. Geopolitics isn't something you can put on a fast-track assembly line.
Exactly. And just to be clear, the source isn't taking a side on those disputes, and neither are we.
Right, we are just looking at the structural delays.
Exactly. The physics of the dam might take 6 years, but the social and political physics of the water rights might take 15. The text uses GERD as a vital structural example of how external, non-engineering friction impacts execution.
Now, as we move through this list, from the modular roof nodes of the airport to the prefabricated sunken tubes of the sea crossings to the pre-assembled turbines of the dams, a very distinct pattern is emerging here.
What's that?
The actual construction site seems to be doing less and less construction.
Oh, yes, you're observing the industrialization of architecture. The site is transforming from a place where raw materials are shaped by craftsmen into basically a final loading dock where massive finished components are simply connected.
Which brings us to the most radical section of our deep dive, the giant Lego revolution.
This is where the numbers get really crazy.
They really do. The text highlights Project 6, broad, sustainable building prefab towers in China. And I have to say, the statistics here broke my brain. We aren't talking about years or even months anymore.
The metrics here truly strain credulity. We're looking at massive, multi-story buildings erected between the 2010s and 2020s.
I'm going to read these directly from the source, the T30 Hotel. 30 stories built in 15 days. That was their benchmark in 2012.
Right.
Then, Mini Sky City, a 57-floor tower, 180,000 square meters of space, erected in 19 days. And finally, a recent 10-story building erected in just 28 hours.
A 10-story building in 28 hours. Think about the logistics of that. It takes longer to get a standard permit approved in most cities than it takes this company to build a mid-rise apartment.
I am looking at the physics here, and I'm honestly struggling. I understand prefabrication. I understand building a wall in a factory and driving it to a site.
Sure.
But a 57-story skyscraper involves massive wind shear, complex plumbing, massive electrical grids. How do you stack 57 floors in 19 days without the entire thing just snapping in half the first time the wind blows?
Because the building isn't a collection of walls and floors being nailed together on site, the methodology is 100% factory prefabricated volumetric modular construction.
Volumetric modular construction.
Yeah. Imagine a shipping container, but instead of steel walls, it's a fully finished room.
Yep.
These modules are built in highly controlled factories. They don't just frame the steel. They pre-install the plumbing manifolds, the electrical wiring harnesses, the HVAC ductwork, the drywall, the flooring, and even the light fixtures before it ever goes on a truck.
So it's less like building a house and more like manufacturing a car on an assembly line.
That is the exact metaphor. The site is just the final assembly point, where the chassis meets the engine. When these massive 3D modules arrive on site, cranes hoist them into place.
But what about the connections? Because if floor 33 is dropped onto floor 32, you can't have a guy with a blowtorch spending a week welding the joints together in the rain.
No welding at all. They use heavily engineered flange-bolted joints.
Bolted.
Bolted. High-tensile steel bolts are inserted into pre-machined holes and tensioned with pneumatic torque wrenches in minutes. The structural frame locks together almost instantly.
Okay, but what about the utilities, like the plumbing and electrical?
It's all plug and play.
Seriously?
Yeah, the plumbing uses manifold systems with flexible, industrial-grade couplings. When the top module lands, a worker simply connects a heavy-duty gasket between the two pipes and clamps it down.
Wow.
And the electrical lines use pre-tested harnesses that snap together like a massive version of an extension cord. Because every single millimeter was mapped digitally and laser cut in the factory, the on-site tolerances are flawless.
That is mind-boggling. You eliminate weather delays because 95% of the work was done indoors.
Exactly.
You eliminate sequential trade delays. I mean, the electricians aren't waiting for the drywallers because they're all working simultaneously on different modules down an assembly line.
Exactly. And the source notes this modular revolution isn't just for vertical skyscrapers. It's being applied horizontally across massive infrastructure, too. It specifically points to high-speed rail expansion and rapid bridge swaps in China in Projects 7 and 8.
They built the world's largest high-speed rail network in a matter of years. How do you apply factory manufacturing to hundreds of kilometers of elevated train tracks traversing mountains and valleys?
Through ruthless standardization. Instead of an engineering firm designing a bespoke, custom bridge for every single valley, they standardized the design of the viaducts, the elevated concrete sections the tracks run on.
Okay.
They mass-produced thousands of identical, massive, prefabricated concrete box girders in localized pop-up factories along the route.
But how do you get a massive 1,000-ton concrete girder onto pillars in the middle of a remote valley?
They engineered specialized equipment, specifically massive bridge-laying machines, like the SLJ 900.
What is that?
These are behemoths. The machine is essentially a massive steel truss on wheels. It drives out onto a completed section of the bridge. It extends a long arm out across empty air to rest on the next empty concrete pillar.
So it turns its own arm into a temporary bridge.
Yes. It then uses internal hydraulic winches to slide the massive prefabricated concrete girder forward along its own frame, lowers the segment perfectly onto the pillar, secures it, and then drives forward over the new section it just laid down to repeat the process.
That's incredible.
It is an infrastructure factory on wheels, crawling across the landscape and leaving a high-speed railway in its wake.
It's mesmerizing to even think about. And this philosophy of modular, heavy-lift execution is what enables the Lubu-style bridge swaps mentioned in the text.
Oh, the Lubu method. That is the pinnacle of minimizing live network disruption. Imagine a critical railway artery. The bridge is aging and needs replacement. The traditional method means shutting down the tracks for months, devastating the regional supply chain, while you demolish the old bridge and build a new one.
Which is a complete economic nightmare for commuter and freight rail.
Absolutely. But with this rapid execution model, they build the entire new bridge, hundreds of tons of steel and concrete on massive hydraulic rollers and Teflon tracks right next to the old bridge, while the trains are still running.
So they build it parallel to the active track.
Yes. Then they wait for a narrow window, often overnight. The text mentions 24 to 43 hours.
What happens in those 24 hours?
Thousands of workers and massive heavy-lift machines swarm the site in perfect synchronization. They cut the old bridge free. Using hydraulic jacks, they literally slide the old massive bridge sideways out of the way.
They just push it out of the way.
Yep. Simultaneously, they slide the fully completed new bridge along the tracks directly into the empty gap. They bolt the joints, reconnect the signal wires, and the morning commuter trains run right on schedule over a brand new bridge.
It's an aggressive industrial ballet. And the source notes in Project 10 with the Alpha Grand Port expansions in Iraq that these techniques, the modular breakwaters, the rapid dredging, the heavy lift execution, are becoming an export.
Yeah, exactly.
Chinese contractors and others are taking this blueprint for speed and deploying it globally.
The capacity to alter geography at unprecedented speed is now a marketable, exportable service.
We have covered immense ground here. We've seen airports erected in 3 years, tunnels weaponizing the ocean's pressure to seal themselves, dams fighting internal thermodynamics with chilled water, and skyscrapers bolting together in 19 days.
It's a lot to take in.
It is. So it is time to zoom out. We are moving to the final synthesis of the source text, the master blueprint and the dark side of speed. If we distill all of this, what is the actual engine driving this reality, and what is the toll it exacts?
Well, the source systematically synthesizes 6 key enablers, the master blueprint, as you said, that make this hyperspeed possible, which is particularly highly visible in the centralized examples.
Let's unpack the blueprint. What is the first pillar?
We've touched on it repeatedly. Prefabrication and modular construction.
Right.
By shifting construction into manufacturing, you defeat weather, eliminate trade sequencing bottlenecks, and ensure laboratory-grade quality control on components.
Makes sense. Pillar 2.
Massive resource mobilization. Speed requires overwhelming force. We're talking about tens of thousands of workers operating in continuous 247 shifts, supported by an unbroken state-backed supply chain that ensures materials arrive exactly when the crane is ready to lift them.
Pillar 3.
Standardization and parallel execution. Refusing the sequential timeline.
Building the roof and the tunnel at the same time.
Exactly. You standardize the viaducts so you don't have to redesign them. You build the terminal roof, the runway, and the subterranean rail tunnels concurrently.
Okay, pillar 4.
Advanced monitoring and technology. This is the nervous system of the site. Digital twins modeling the steel nodes before they are cut. Automated bridge-laying machines. Real-time digital thermometers pumping chilled water through concrete.
Killer 5.
Economies of scale. When you commit to a 30,000-kilometer high-speed rail network, the first 100 kilometers are difficult.
Sure.
But by the 1,000th kilometer, the workers, the factories, and the machines have optimized the process to a cellular level. The scale itself generates the speed.
And the final pillar, which seems to underwrite all the others.
Governmental priority and reduced bureaucracy. The administrative void.
Right.
When a centralized authority declares a project paramount, the friction of land acquisition, environmental injunctions, and funding debates vanishes. The path is cleared by fiat.
Okay, that is a formidable blueprint. It is an optimized machine for bending reality. But here's where I must play devil's advocate.
Let's hear it.
Because reading that list, my alarm bells are deafening. Speed is thrilling, but physics, economics, and human endurance are finite resources.
Yeah.
You cannot cheat the system without a bill coming due. What is the true cost of this velocity?
The source text does not flinch from the reality of that cost, actually. It explicitly outlines the severe caveats and trade-offs required to maintain this pace. The dark side of speed is very real.
Let's face that reality check. What is the most immediate cost?
The human cost. The text explicitly notes that speed trades off against safety, acknowledging fatalities on some of these hyper-accelerated projects.
Oh, wow.
Think about the reality of Pillar 2 massive mobilization and 247 shifts. When you have 40,000 workers operating heavy machinery, hoisting 500-ton concrete blocks at 3.0 VM under stadium lights, and the singular mandate from above is speed, well, human fatigue becomes deadly. The margins for error vanish.
It's chilling to think about. The speed is quite literally extracted from the physical endurance and safety of the labor force. What about the structures themselves? Does speed compromise the concrete and steel?
The source lists quality and sustainability issues as a primary caveat. While factory prefabrication helps, the relentless pace of on-site assembly can lead to cut corners.
Naturally.
There are numerous historical instances where hyper-rapid construction led to long-term structural flaws, water intrusion, or catastrophic maintenance nightmares down the line. If a highway needs to be completely rebuilt in 7 years because the subbase was rushed, the initial speed was just a financial illusion.
Speaking of finances, I'd assume building fast saves money, but is that true at this scale?
Rarely. The text highlights massive debt risks. To mobilize specialized bridge-laying machines and 40,000 workers instantly requires astronomical upfront capital.
Right.
Often, this means governments or entities take on crippling debt, operating on the assumption that the new airport or rail line will instantly generate massive economic returns. If they build ahead of actual demand and the passengers or freight don't materialize, that debt can suffocate regional economies for generations.
And then there is the Earth itself. You can't flatten hills, dam rivers, and dredge the ocean in a few years without the ecosystem absorbing a massive shock.
Severe environmental impact is a final glaring trade-off. Traditional infrastructure moves slowly, largely because of environmental impact studies, tracking water tables, migratory patterns, and pollution risks.
Right.
When you prioritize pure speed, you frequently bypass or compress these studies. The long-term disruption to local hydrology or biodiversity is simply accepted as collateral damage for economic progress.
So we have the breathtaking blueprint for speed and the sobering reality of the costs, worker safety, potential quality degradation, staggering debt, and environmental shock.
Yeah.
And this leads to a fascinating structural observation the author makes at the end of the text.
Yes, it does. The source draws a distinct comparison between systems. It points out that Western or highly democratic projects often face intense regulatory, environmental, and labor constraints, which inherently stretch timelines into decades. Conversely, the fast projects we've discussed rely heavily on an authoritarian-scale coordination that simply is not structurally compatible with other systems.
And looking at this objectively, based on the text, it's not about declaring one system a utopia and the other a failure.
Exactly.
It's about recognizing how different societies engineer their priorities. A system with mandatory environmental review periods, unionized labor protections regarding shift hours, and multi-stage democratic voting on municipal debt is fundamentally engineered to move slowly.
Yes.
Those delays that frustrate commuters are often safety mechanisms, what we might call protective friction functioning, exactly as designed to protect the worker, the taxpayer, and the environment.
Conversely, a centralized system can strip away that protective friction. This results in awe-inspiring physical achievements that can catapult a society's logistics and economy forward by decades, in just a few years.
But it comes with risks.
Absolutely. It requires accepting concentrated top-down control and the heavy systemic risks that come when the safety brakes are removed. It is a profound, defining societal choice.
Protective friction. I love that concept. As we wrap up this deep dive, I want to bring this back to you, the listener. Being truly informed about modern infrastructure means looking past the flashy headline of a 19-day skyscraper.
Right, look deeper.
It means understanding the complex, often hidden machinery beneath that fact.
It requires acknowledging that we now live in an era where massive physical environments actually can be altered in the blink of an eye. The engineering capacity exists, the material science is proven,
Yeah.
but it requires a society willing to orchestrate unimaginable logistics and pay the inherent heavy toll required to bend the physical world to immediate human will.
The capability is no longer the bottleneck. The willingness to endure the systemic cost is. And that leads to a final lingering thought I want to leave you with, building on the author's opening premise.
We started with the Age of Abundance, which currently relies heavily on massive manual labor and centralized top-down control to achieve this speed.
Right.
But as we look 5, 10, 20 years into the future, as AI masters logistical supply chains flawlessly, as advanced robotics increasingly replace human labor in dangerous 3.00 AM heavy lift operations, and as material science creates even smarter concrete,
Yeah.
will technology eventually bridge this gap? Will we reach a point where the entire world can achieve these breakneck construction speeds safely, eliminating the dark side without needing the protective friction to slow us down?
Or is the physical reality of our planet ultimately too stubborn? Will extreme speed in manipulating millions of tons of earth and steel always inherently carry a heavy human and environmental cost that simply cannot be coded or engineered away?
It's a massive question.
It really is. It's a question of whether our brilliant machines can ever truly conquer the laws of nature, or if the Earth will always demand a toll for our impatience. Think about that the next time you drive past a construction site and see a crane swinging against the sky. Thanks for taking this deep dive with us.